Hello everyone, I'm Zhang Ningyu from Alibaba Group. I will present our paper, Relation Adversarial Network for Low-Resource Knowledge Graph Completion. Knowledge graph organize facts in a structured way as triples. However, knowledge graphs are usually far from complete and noisy. Thus, various knowledge graph completion methods have been proposed in recent years. Knowledge graph completion could be achieved either by link prediction via typical knowledge graph embedding models such as Chen, or by relation extraction models which aim to complete missing relations by extracting new relational facts from textual corpus. One of the main difficulties for knowledge graph completion is the long tail and low resource problems. As shown in the figure, the blue line shows there is a large portion of relations having only a few triples. The red line shows that the prediction results of relations are highly related to their frequency, and the results of low-resource relations are much worse than those of highly frequent ones. Relation extraction suffers the same difficulty. The green line shows there is a large portion of relations in NYT having relatively low numbers of labeled sentences, and the prediction results decrease severely for those long-tail relations. There are two main different approaches for the low-resource knowledge graph completion problem. Some researchers propose to learn a more robust representation via transfer learning, adversarial training, or mental learning in the X-short learning style. Also, some researchers propose to generate more data by rule learning or neural rule grounding. Inspired by the idea of domain adversarial network for domain adaptation, it is intuitive to adapt knowledge and features learned from high-resource relations to a different but related low-resource relation. However, there is outlier source relations that might cause negative transfer. For example, the model expected to learn general location information from three source relations: place of death, place of birth, and country, and then adapt knowledge to the target relation, place of burial, to improve its prediction performance. However, the source relation capital may result in negative transfer to the target relation, place of burial, as capital does not describe a relation between a person and a place. We notice that learning general relation invariant features can transfer knowledge between relations, and different relations have different contributions. Motivated by this, we propose a general framework called Weighted Relation Adversarial Network with two different knowledge graph completion tasks, namely link prediction and relation extraction. Our approach consists of three modules: instance encoder, which learns transferable features that can disentangle linguistic variations across relations, and adversarial relation adaptation, which can distinguish among samples having different relation distributions, weighted relation adaptation, which can identify unrelated source samples and downweight their importance automatically to tackle the problem of negative transfer and encourage positive transfer. Specifically, we utilize different encoders for link prediction and relation extraction. We implement the instance encoder with CNNs, given both model performance and time efficiency. Adversarial domain adaptation has been successfully applied in transfer learning. The core idea is to extract domain invariant features via an adversarial learning procedure that can reduce the distribution discrepancy between the source domain and the target domain. Inspired by adversarial domain adaptation, we propose a relation adversarial network which consists of two adversarial players, the feature extractor F and the relation discriminator D. We also propose weighted relation adaptation to evaluate the significance of each source. Firstly, we average the label predictions of all target data from the source classifier as relation weights. The intuition here is that the probability of assigning the target data to the source outlier relations is sufficiently small. And secondly, we utilize a pre-trained malicious relation discriminator for instance weights learning. The concept is that the sample is likely to be non-transferable if it can be almost correctly discriminated from the target relation by the discriminator. And moreover, it is obvious that the weights of different granularity have different contributions. Thus, we propose a relation gate mechanism to balance the instance and relation weights. This is overall our approach. Relation adversarial training can transfer knowledge, and weighted relation adaptation can eliminate the negative transfer. And we conduct our experiments for link prediction and relation extraction on 4 datasets, and all datasets are publicly available. Firstly, from the entity prediction results, we can observe that our approach can achieve lower mean rank than baseline models, and we also find that the improvement of our approach on FB 1.5M is larger than FB 15K237 because FB 1.5M has more source relations which can leverage more knowledge. And moreover, our approach also achieves the best results in triple classification. For the relation extraction on ACE, we have two settings. The first experiment takes a standard adaptation setting. We find adversarial learning is effective for learning domain invariant features to boost performance. And the second experiment takes the partial adaptation setting. We only choose a part of relations as target, and our model also outperforms the plain adversarial adaptation model. Our approach achieves the best performance on NYT dataset among all the other unsupervised adaptation models. We also add labeled data in the target domain, and our model with 100% labeled data outperforms both CNN, PCNN, and rank EX attention. To better demonstrate different strategies in our model, we conduct ablation studies. And we find the performance degrades when we remove relation gate, relation weights, or instance weights. And we also conduct experiments to analyze the balance between instance and relation weights. The instance and relation weights have different influences on the performance. And we also find the relation weights have relatively more influence on the performance for most of the relations. And we also conduct experiments to analyze the negative transfer. We observe that our approach performs better when the number of target relations decrease, and our approach achieves comparable results in standard setting. This means the weights mechanism will not wrongly filter out relations when there are no outlier relations. We also give some examples of how our relation gate balance weights for relations and instance. We display the alpha of different relations. For the relation of, there are lots of dissimilar relations, so relation weights are more important. For relation educated in, the instance difference is more important, so the alpha is very large. Moreover, we also observe that our model can automatically find outlier relations or instance. In other words, our work disentangles the relation agnostic and relation-specific representations, and knowledge transferring is beneficial for the tail. We also find that not all knowledge are useful. Some knowledge may cause negative transfer. To conclude, we present a general framework called Weighted Relation Adversarial Network to learn relation invariant features. We present a relation-gated mechanism that fully reflects the shared label space assumptions. Experiments showed that our framework achieved a set of results in low-resource settings on public benchmark datasets. Thank you for listening and welcome to scan our QR code to get our data. Thank you.